welcome back. Guess what I learned how to do? I learned how to put lines in the thing. Isn't that cool? Maybe now I won't be all wonky and at some crazy ass angle. I probably will be still, but you know what? Maybe it'll make it better. Maybe it'll make it better. Okay, let's do a little test here. Okay, let's do a little test from the last example. Okay, let's calculate the pH using the let's calculate the pH within the equilibrium step using the Henderson-Hasselbalch equation rather than using an ice table. Okay, so let's go back to this equilibrium step from above. Let's see, we have initial concentrations are approximately 0.100. Ka is approximately 10 to the negative 5. The difference between these two is 10,000 times, right? This is a 10 to the 4 difference. So in this case, the Henderson-Hasselbalch is an excellent choice to use here. Okay, so the Henderson-Hasselbalch is valid. Okay, so let's use that. So Henderson-Hasselbalch pH is equal to negative pKa plus log of A minus divided by HA. pH is equal to negative pKa, so that would be negative, oh wait, not negative, it's not negative pKa, sorry, it's just pKa. So that becomes negative log of 1.8 times 10 to the minus 5 plus the log of 0. Let's see, A minus was 110 divided by 0.090. Okay, so we still have to do that first stoichiometry step to find these values, but we don't have to do the ice table here. So you end up with 4.83 as the pH using this equation, and it turns out that this is exactly the same pH as we had originally using the ice table. Okay, up here, whoa, what the heck? Okay, up here, this is the same pH as what we got below using the Henderson-Hasselbalch. But the Henderson-Hasselbalch was way easier. Okay, so sometimes when these conditions here are met, sometimes it's a lot easier to use the Henderson-Hasselbalch rather than go through the ice table nonsense. Okay, so we just did the pH of a buffer with a weak acid at its conjugate base. What if we make a buffer with a weak base and its conjugate acid? How does that change it? Wait, that's okay. pH of, let's see, pH of a buffer with weak base and conjugate acid. Okay, so this is basically the opposite of what we've been doing already. This is a very similar procedure as weak acid and conjugate base. It's just kind of the opposite because you have a weak base and a conjugate acid. Okay, let's do this with an example. Let's look at a buffer that we make by mixing 0.50 molar ammonia. Ammonia was right. And let's see, 0.20 molar ammonium chloride. See, I'm still doing the line going up. See, I'm still at an angle. Huh. You know, I even do that on the board. I'm sure you guys remember. I would even draw at an angle on the board. So maybe my brain is at an angle or something. Who knows? The equation or the chemical reaction between these two is ammonia reacts with water to form ammonium and OH minus. Okay, so it pulls one of those hydrogens off the water to form OH minus, and the pKb for this guy is equal to 4.75. Okay, PKB is equal to 4.75, which means that KB is equal to 10 raised to the negative 4.75 is equal to 1.8 times 10 to the minus 5. Okay, so this is very small. That means that x is small. Approximation is valid. Okay, so x is small, approximation is valid because KB is pretty tiny in comparison with the initial concentrations. Now we know that pKa plus pKb is equal to 14.00. Remember that relationship we derived earlier? That means that pKa is equal to 14.00 minus pKb. Okay, so then we get 14.00 minus what was our pKb? 4.75. 4.75. The pKa is equal to 9.25. Okay, so now we have a pKa. pKa is equal to 9.25. We can use the Henderson-Hasselbalch equation here. So we're going to use Henderson-Hasselbalch, and we get a pH. This is the pH of the pure buffer, by the way. pH is equal to pKa, 9.25, plus log of the initial concentrations of A minus, which in this case would be 0.50 molar, divided by, let's see, A minus, A minus is the base, over the acid 0.20 molar, and we end up with a pH equal to 9.65. Okay, so this buffered solution has a pH of 9.65, and you can kind of see that there will be a bunch of different buffered solutions that have different pHs that kind of range all over the place, depending on the system that you initially look at. Okay. I think actually I'm going to stop here. I know I didn't really do much in the second part, but the first part I actually went way too long. I went for like 35 minutes in the first one. So I'm going to stop here because the next part would be better if we just cover that all in one session rather than break it up. Yeah, I think that's what I'll do here. Okay, so we'll stop there. I hope you guys have a great Monday. Yeah, and if you have any questions on the upcoming assignments or tests or final or anything, please be sure to shoot me an email. All right? Hope you guys have a good day, and take care.